All right, Theorem 8. If the partial derivatives of f with respect to x and f with respect to y exist near a, b, and are continuous at a, b, then f is said to be differentiable at a, b. And so all we're going to do now is look at example 2. We're going to tell if it's differentiable given the theorem, and then we're going to find the linearization of the function at the point. So let's go ahead and first take the partial derivatives and see if they exist near our point 3, 0. So taking the linear approximation, or not linear approximation, so taking the partial derivative, the first one we want to do is take the partial derivative with respect to x. So the partial derivative with respect to x is equal to, so again, another way of looking at f of xy is x plus e to the 4y, all that to the 1/2. And so that's what I'm going to use to take the derivative with respect to x. So 1/2 x plus e to the 4y to the negative 1/2 times the derivative of the inside, which is going to be 1. So we're just left with 1 over 2 square roots of x plus e to the 4y. All right. Now, what we want to do, well, here, I'll do the partial derivative with respect to y first, and then we're going to evaluate both, and I'll evaluate both on the right. So the same thing, we're going to take the partial derivative, in this case, with respect to y. So the first part stays the same, but now we can actually take the derivative of e to the 4y. And the derivative of e to the 4y is just 4e to the 4y. So times 4e to the 4y. Cleaning this up, half of 4 is 2, so 2e to the 4y over radical x plus e to the 4y. And now what we're going to do is we're going to find, okay, are those defined at that value? And so the partial derivative of x at 3, 0 is going to give, so I go ahead and plug that in. I'm going to get 1 over 2 times radical. Then I have 3 plus e to the 4 times 0, which that's going to give me 1. So 3 plus 1 is 4. 2 to 4 is 2. So then at the point 3, 0, the partial derivative of x is just going to give me 1/4. And then check it with y at 3, 0. I'm going to plug in and get 2 times e to the 4 times 0 over the square root of x. In this case, is 3 plus e to the 4 times 0. And the denominator is going to give me square root of 4, which is 2. 2 is going to cancel out. E to the 4 times 0 is just 1. And so they're going to get 1. All right, so they're both defined. Both our partial derivatives are defined at the point 3, 0. So by Theorem 8, we're going to be able to tell that this function is differentiable. So I'm going to go ahead and write that for you. So this is how you would write it if I ask both f sub x, or both f, the partial derivative at both partial derivatives are continuous functions near our point 3, 0. So f is differentiable at 3, 0 by Theorem 8. I'm just going to put cap T 8. That's by Theorem 8. Just so I can save some room. Whoa, that's not the highlighter. Alright, so now let's go ahead and do, I already use purple, let's use blue. All right, so now we want to find the linearization of the function at that point. So again, if you recall, the linearization is going to be capital L of xy is equal to f of three zero. So our initial z value plus our partial derivative of x at 3 0 times x minus 3 plus our partial derivative with respect to y at 3 0 y minus 0. I'll go ahead and just put that there, and I can clean it up because there's still some more that I need to do. All right, so to get this value right here, we're just going to substitute in 3 0 into our function there. All right, so I'm just going to go ahead and do the math there. 3 plus e to the 0, so 3 plus 1 is 4. 4 and the square root of 4 is just 2. So we're going to have 2 plus, and then at the partial derivative at 3 0 with respect to x is 1/4. We found that. And then we have x minus 3. The partial derivative of y at 3 0, we found that to be 1. So it's just 1 times y. All right. Now let's go ahead and clean that up. And we're just going to combine our like terms. So we're going to get 1/4 x plus y, negative 3/4, 2. So it should be 5. I believe, yeah, it should be 5/4. All right. Again, this is the linear approximation or the linearization at the point 3 0. All right, example 3. So now I'm not going to really give you any of these to work on. It's just showing you how we can use linearization to help us find, and say instead of being able to take the derivative of some function or the partial derivative of some function, we're going to be working with a table, and just like from I guess last class, so yesterday, there's a way to actually find, what would be a good approximation of the change between 2 points, and so that's what we're going to do. All right, the wind chill index W is the perceived temperature when the actual temperature is T, and the wind speed is V. So we can write W is equal to F of cap T of V and V. The following table of values is an excerpt from Table 1 in Section 14.1. Use the table to find a linear approximation to the wind chill index when T is near negative 15 degrees and V is 50 kilometers per hour. So I'm going to highlight those real quick. So T, negative 15, and then we have 50 kilometers per hour, so right there. Then estimate the wind chill index when the temperature is negative 17 degrees Celsius and the wind speed is 55 kilometers per hour. All right, so the first thing we want to do is we're going to denote what our actual value is when we have negative 15 degrees Celsius for our temperature and 50 kilometers per hour for velocity. So we have F of negative 15, 50, and that's equal to negative 29. Now to estimate our T, it's like taking the partial derivative with respect to T for negative 15 and 50, all right? And then we're going to do the same thing for velocity at negative 15, 50, our point. And we follow the same procedure we did in 14.3. So what we'll have is we'll have the limit as h approaches 0 of f of negative 15 plus h. Let me write that a little bit better. Negative 15 plus h. 50 minus f of negative 15, 50 all over our h. And then our steps for this, because our temperature goes in increases of 5, h is going to be plus or minus 5. All right, so let's go ahead and approximate. So we're going to do the first one. So negative 15, 50, and approximating it, we're going to have f of negative 10, 50. Because our first value we said is going to be positive 5. So, over here I can say when h is equal to 5. All right, and then the next one's going to be when h is equal to negative 5. Minus f of negative 15, 50 over h. And so negative 10, 50 is going to give us negative 22 minus, we found that negative 1550 is going to give us negative 29 all over 5. And when we solve, we're going to get 1.4. All right, same thing, but now h is negative 5, so we're going back 5. We're going to have negative 20, 50. I'm sorry, I'm going to keep that negative 15 because we're approximating it, but we're going to use f of negative 20, 50 minus our initial f divided by h. And so here we're going to get negative 23 minus negative 29 divided by, in this case, a negative 5. I don't know. Well, I used the wrong way. It should be negative 35. Went across my velocity instead of going down on my t. And here we're going to get an approximation of 1.2. Then averaging these two values out, we're going to get the partial of t is at negative 1550 is going to be 1.3. Just adding the 2 and dividing by 2, or you're noticing that 1.3 is between the two. All right, we're going to do the same thing, but for our velocity. And so instead of having to rewrite the whole thing again, I'm just going to go ahead and do velocity. So f of v, and hopefully you understand where it's coming from, negative 1550. But now we're going to be dealing with our v value, so we're changing this value. And our steps for that is going to be, because for our velocity they increase and decrease by 10, we're going to do h is equal to 10, and h is, let me go down a little bit further, h is equal to negative 10. All right, and so now we have f of negative 15, and we'll do 60 minus f of negative 1550 all over h. And so negative 1560 is going to give us negative 30. So negative 30 minus a negative 29 all over 10 is just going to give us negative 0.1. And then doing again, but when h is negative 10, so we have f of negative 1540 minus f of negative 1550 all over h. And so in this case, we're going to get negative 27 minus negative 29 all over negative 10. We get negative 0.2. So averaging those two out, we get our partial with respect to v, and that's going to be negative 0.15. Right? Based off of this, a linear approximation to the wind chill index function is going to be given as so. So let me change again. So our function f, let me lowercase that v a little bit. Cap t of v is approximately, and so we're going to take our value at negative 1550. We're going to add that to our partial of t at negative 1550 times t minus our initial x value, or not our initial t value, which is negative 15, not our initial x. Let me block those off. Plus our partial of v at negative 1550. And that's going to be v minus our initial v, which is 50. All right. And now we're going to go ahead and plug in. So f of negative 1550 we said was negative 29. F of t is 1.3 times t plus 15 plus f of v. Oh, I didn't. Okay, I realized I did not write that down correctly. So let me change this up real fast. So our partial of v at negative 1550 is negative 0.15. And so negative 0.15 and then v minus 50. And so now we're going to go ahead and do the math. And, instead of simplifying it even further, I'm just going to go ahead and leave it there. So here's our linearization, just because we don't really want to multiply 1.3 times 15 and negative 0.15 times 50 and clean that all up. So it's okay to leave this as it is. And we're going to use this to approximate, and then what's the question asking? Then estimate the wind chill index when the temperature is negative 17 degrees Celsius and the wind speed is 55 kilometers per hour. All right. So I'm going to do f of negative 17 and v is 55. I'm going to plug that in, so negative 29 plus 1.3 times negative 17 plus 15 plus negative 0.15 times 55 minus 50. And then we're able to approximate that. And so our approximation, again, let me use my squiggles here. So our approximation is going to be, plugging that into a calculator, negative 32.35. And so that's going to be our estimated wind chill index, so negative 32.35 degrees Celsius. Let me